All right, so now that we've talked about sphere inversions, we're going to talk about the stereographic projection. And what's going to turn out to happen is that you can think of stereographic projection as being essentially a special case of sphere inversion restricted to something else. Okay. So let me sort of give you sort of a picture of what stereographic projection normally is interpreted as. So what happens is that this is, of course, one of the many ways you could try to project, say, parts of the surface of the sphere into a two-dimensional space. Right? So the picture you should have in mind here is that you have a sphere of radius 1. It's like centered at the origin, all right, and you want to map at least part of that sphere, say the northern hemisphere of that to the plane. Okay. So what you're going to do then is that you're going to, so if you project from the North Pole, okay, so this is the point, let's say 0, 0, 1, it's like in this realization in three-dimensional space. So what you do is that you look and you want to project, say, a point that's like on this sphere, let's call that x. Okay, what you do, of course, is you draw a line through the North Pole and that point, and you sort of keep going until you hit the plane. Okay, and that's where you put where you map that point x in the sphere to the plane. Okay, so this is the way you normally think about it. So it turns out that you can also interpret this in terms of sort of sphere inversions, and sort of the way to sort of think about this then has to do with the fact that if you recall with sphere inversions, right, it maps in general d-dimensional spheres to d-dimensional spheres. Okay, so if you have this d-dimensional sphere, the D plane is in some sense a degenerate case of the D sphere. So at least in principle, you might think that this is sort of in the right setting where the normal stereographic projection maps, in this case, the two sphere to the two plane. Okay, and maybe you want to do something similar, but you want to interpret it in terms of sphere inversions. Okay, all right. Okay, so how we're going to do this is that we're going to look at inversions. We're going to look at inversions which are not just about unit spheres centered at the origin. Okay, so inversions can be defined relative to any center. Let's call that Z in RD plus 1, and radius in any radius R greater than equal to 0. Okay, so that is sort of the inversion, but I'm going to put a Z and R there as parameters, and what it does is that the answer is the radius R times the normal inversion map which we defined before, but I shift the point x so that it's centered about z, okay, and then I scale it by r, okay, and then I apply the sphere inversion, and then I multiply it by r again, and then I move it back to z. Okay, so this is how sort of I conjugate it's like the sphere inversion formula so as to give me what I want. Okay, so now essentially what happens if you think about this is that the North Pole gets mapped to infinity in the usual stereographic projection. So you obviously, if you want to interpret this stereographic projection as a circular inversion, right, then it has to be that the center, if you will, of the circle which you're inverting respect to is at the North Pole. Okay, so we consider the case where the center is n, okay, and then now n just doesn't have to be in three-dimensional space, it could be in d plus one dimensional space. Okay. All right, the North Pole of SD. Okay, and then the radius is going to be square root of 2. And if you're wondering why we did that, it's because if you think again about the usual sphere, the usual stereographic projection, this circle here, right, is fixed by stereographic projection. Okay, so if you have something which is centered at this point, it's like the North Pole, then what has to happen is that you have to have some sort of sphere, okay, which you're doing the sphere inversion about, right? But that sphere has to intersect the plane along the equator of the unit sphere, and you can then easily check that that radius has to be square root of 2, right? Because this is radius 1, this is radius 1, so this is square root of 2. Okay, so this is what motivates our particular choice of what you're doing sphere inversion with respect to the North Pole and respect the sphere radius square root of 2, so that the intersection of that sphere radius square root of 2 centered around the North Pole with the plane is exactly the equator of SD. Okay, so so this then means that the equator of SD, right, is fixed by this inversion. Okay, and actually it's like if you sort of extend the stereographic projection to the southern hemisphere, right, then essentially what happens is the following. If you take this point and you look at where that line intersects the it's like again the plane, right, you get the extension of the stereographic projection into the South Pole as well. Okay, so it really does map, if you will. It's like the entire sphere, it's like to the plane. It's like, again, modulo these issues with what happens near the North Pole here. Okay, all right. So again, the equator of SD is fixed by this inversion. Okay, and then the image of SD, right, is the D plane, where the D plus first coordinate vanishes. So again, in this example, it's where the Z component is 0. Okay. All right, so that sort of is almost everything you need. It's like you're looking at a particular sphere inversion with its particular center, which is at the North Pole, and radius square root of 2. All right, and of course this is really defined from RD plus 1 to RD plus 1, but in stereographic projection you tend to restrict it just to the d-dimensional sphere, and then you identify it with this d-dimensional plane. Okay, so we'll do that. So then the stereographic projection is the restriction of this particular inversion to the unit sphere SD, and I'm going to denote this by S, but sort of a Greek S. It's basically a sigma. Okay, so it's mapped from SD to, well, SD excluding the origin. Sorry, excluding the North Pole. Okay, to RD. Okay, so I'm going to think of this d-dimensional plane as just being identified with RD. Okay, by sort of essentially ignoring the last coordinate, which is always 0. And this is defined by sort of this S of x, right, is equal to the inclusion or inversion map centered about the North Pole with radius square root of 2 applied to x, and then there's, I guess if you will, it's like that sort of a projection, if you will. It's onto RD. Okay. Okay. So as is the case with the usual stereographic projections, this will preserve spheres. Okay. So there's a stereographic projection lemma, which sort of, in some sense, fairly obvious. It's like it's a fairly obvious consequence of the usual sphere inversion lemma. Okay. So let me just state it. So the stereographic projection lemma is that, let's say that I have sigma prime now, okay, be a d minus 1 sphere. So I'm going to think of spheres on the d sphere, okay, on SD, okay. And then if the North Pole is not an element of this d minus 1 dimensional sphere, then stereographic projection applied to sigma prime is again a d minus 1 sphere, right? And then if the North Pole is an element of that sphere, then stereographic projection applied to this, right, is a d minus 1 dimensional plane. Okay, and this really just comes from the fact, if you will, that every one of these d-dimensional spheres is like which are floating around here really are the intersection of a d sphere and this particular unit sphere, right? So this comes from the fact that every d minus 1 sphere in SD is the intersection of a d sphere with SD. Okay, so obviously, so its image is the intersection of the image of SD, which is, of course, it's like this D plane, of RD with the image of the D sphere. And of course, we are again, it's like having this usual thing where you think of the D plane as being a degenerate D sphere. So if n is in this sigma prime, right, then basically what happens is that the image, it's like of n, if, well, the image of, okay, so let me say it this way. Okay, so if n is in sigma prime, then sigma prime itself, right, is the intersection of a deep sphere sigma with SD, but then obviously n is contained in sigma, and so when you take sigma and you map it by sort of this particular sphere inversion, right, then what ends up happening, if you will, is that you will get a D plane, and then you take the intersection of a D plane of another D plane, you get a D minus 1 plane, which is what you have here. So again, it's like this is not so surprising. The stereographic projection lemma is not so surprising, and it's really just a consequence of what you already know. It's like from sphere inversions, images of sphere inversions, together with the observation that every D minus 1 dimensional sphere in SD can be expressed as the intersection of a D sphere with SD. Okay, and then once you put those pieces together, then this is sort of a trivial consequence of the stereographic projection lemma. So let me just stop here for now.